Welcome to G Fun Facts Online. Today, we're journeying 1.4 billion kilometers from Earth to a small moon that has completely rewritten the rules in our search for alien life. Forget Mars for a moment. Our destination is Enceladus, a tiny, ice-covered world orbiting Saturn. Once considered a minor object, Enceladus is now perhaps the most compelling place in our solar system to look for life beyond Earth. Why? Because beneath its brilliant white surface, it hides a global ocean of liquid salt water. And this ocean isn't quiet. It's actively blasting enormous geysers of water vapor and ice into space, carrying tantalizing clues from its hidden depths. We've sampled these plumes, and what we've found is staggering: the fundamental building blocks of life. This is the story of how a tiny point of light became a prime candidate for a second genesis. Our understanding of this incredible moon is almost entirely thanks to one of the most successful space missions ever launched, NASA's Cassini spacecraft. Launched in 1997, Cassini arrived at Saturn in 2004 for a 13-year tour of the ringed planet and its many moons. Initially, little Enceladus, at only 500 kilometers in diameter, wasn't the star of the show, but scientists knew something was odd about it. Its surface was too bright, too reflective, and it seemed to be feeding Saturn's faint E-ring with material. In 2005, Cassini flew by and confirmed this suspicion in the most spectacular way possible. Its instruments detected massive plumes of water vapor and ice erupting from the moon's south pole, jetting out from huge fissures nicknamed tiger stripes. This was the watershed moment. Enceladus instantly became a top priority. Over the rest of its mission, Cassini performed over 20 flybys, sometimes diving directly through these plumes. This was an incredibly audacious move, allowing instruments like the Cosmic Dust Analyzer and the Ion and Neutral Mass Spectrometer to literally taste the material erupting from an alien ocean. This gave us a direct line to analyze a subsurface ocean on another world, an opportunity unparalleled in the history of space exploration. The data Cassini sent back before its mission ended in 2017 is still being analyzed today, and it continues to reveal a world more amazing than we ever imagined. So what exactly did Cassini find inside those plumes? The data confirmed that Enceladus has a global ocean of liquid salt water, hidden beneath an ice shell about 25 kilometers thick. The ocean itself is thought to be around 10 kilometers deep. The very fact that the plumes contained salt was a huge clue. If the water was just melted surface ice, the freezing process would have pushed the salt out, leaving nearly pure water ice. The ocean-like saltiness strongly suggested a direct connection to a large, liquid body of water. Further analysis revealed this ocean is moderately alkaline, with a pH between about 8 and 9, very similar to Earth's oceans and considered quite friendly for life. It's also rich in dissolved gases like carbon dioxide and ammonia. But how does an ocean stay liquid so far from the sun? The answer is tidal heating. Enceladus is in a gravitational dance with a larger moon, Dione. This tug-of-war forces Enceladus into a slightly elliptical orbit. As it moves closer to and farther from Saturn, the planet's immense gravity squeezes and stretches the little moon. This constant flexing generates friction and heat in its core, keeping the vast ocean from freezing solid and powering the geological activity that creates the plumes. This is where the story gets truly electrifying. The most significant discovery from the Cassini data was the presence of organic molecules in the plumes. Now, when scientists say organic, they simply mean molecules containing carbon, which is the backbone of all life as we know it. Finding them doesn't mean finding life, but it's a critical prerequisite for a world's habitability. As early as 2008, Cassini detected a surprisingly high density of organic materials. But a key question remained: were these molecules genuinely coming from the ocean, or were they being created in space after the plumes erupted? The ice grains in Saturn's E-ring fed by Enceladus, can be hundreds of years old, giving them plenty of time to be zapped by radiation and chemically altered. Scientists needed to analyze fresh material. The breakthrough came from data taken during a very fast flyby. Ice grains smashed into Cassini's detector at over 18 kilometers per second. This high-speed impact shattered the grains in a unique way, allowing the instrument to see past the overwhelming signal of water and clearly identify the organic compounds locked inside. The results were a smoking gun. The freshly ejected ice contained the same organic precursors for amino acids found in the older ring material, proving they were indeed cooked up inside Enceladus Ocean. Not only that, the analysis revealed a whole new suite of complex molecules, including types that on Earth are involved in creating lipids, the fats that form cell membranes. This rich, complex inventory of homegrown organics suggests that Enceladus might have its own prebiotic soup, the kind of chemical environment that could lead to the origin of life. The evidence for habitability gets even stronger when we dive to the bottom of this dark global ocean. Data from Cassini strongly suggests the presence of hydrothermal vents on the seafloor, just like the ones we find in the deepest parts of Earth's oceans. How do we know? The first clue was the detection of tiny nanoparticles of silica, basically microscopic grains of sand, in the plumes. The only known way to form these particles is when very hot, alkaline water, supersaturated with minerals from a rocky core, suddenly mixes with colder ocean water. This implies water temperatures of at least 90 degrees Celsius at the seafloor. But the biggest piece of evidence is the detection of molecular hydrogen gas. Here on Earth, hydrogen is a common byproduct of a process called serpentinization, where hot water reacts with rock in hydrothermal systems. Finding hydrogen in the plumes of Enceladus is a huge deal. Why? Because on Earth, these vents are oases for life, supporting entire ecosystems that thrive without sunlight. Instead of photosynthesis, they use chemosynthesis. They eat chemicals. The hydrogen and other chemicals from the vents are the fuel. The discovery of hydrogen means there is a source of chemical energy in Enceladus Ocean, a free lunch for any potential microbes. In fact, the amount of hydrogen and carbon dioxide detected seems perfect for a type of microbe called a methanogen. These are some of Earth's most ancient life forms. They consume hydrogen and carbon dioxide and release methane as waste. And guess what? Methane is another one of the gases Cassini found in the plumes. So let's recap. To be considered habitable, a world needs three key things: liquid water, a source of energy, and the essential chemical elements for life. The big six elements, often remembered by the acronym CHNOPS, are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Let's run down the checklist for Enceladus. Liquid water? Check. A global ocean. Energy? Check. Chemical energy from hydrothermal vents. What about the CHNOPS elements? Carbon is there in the organic molecules and carbon dioxide. Hydrogen is in the water and as a free gas. Nitrogen is likely present as ammonia. Oxygen is in the water and carbon dioxide. For a long time, phosphorus and sulfur were the missing pieces. But just recently, a reanalysis of Cassini data found definitive evidence for phosphates in the plume ice grains. This was the final, crucial ingredient. Phosphorus is absolutely essential for life as we know it. It forms the backbone of DNA and RNA and is critical for cell membranes and energy transfer. With the confirmation of phosphorus, Enceladus Ocean appears to have all the raw chemical ingredients needed to build and sustain life. Cassini gave us a tantalizing glimpse, but it couldn't see everything. It told us Enceladus is habitable, but it couldn't answer the ultimate question: is it inhabited? To find out, we need to go back with instruments specifically designed to look for life. The scientific community is buzzing with proposals. The European Space Agency is considering a lander mission. NASA is developing concepts like the Enceladus Orbilander. an ambitious probe that would first orbit the moon to study the plumes in incredible detail, and then land on the surface for a 2-year mission to search for biosignatures, the chemical traces of life. Imagine a probe scooping up the fresh snow falling from the plumes and analyzing it for complex biological molecules. While these missions are likely decades away, the prospect of returning to Enceladus with the explicit goal of finding life is one of the most exciting frontiers in science. The discoveries at Enceladus have forced us to rethink where life could exist. For so long we were focused on rocky planets in the habitable zone close to a star. But Enceladus shows us that habitable environments, powered by internal heat, can exist in the cold, dark outer reaches of a solar system. This opens up countless other icy moons, both in our solar system and orbiting distant stars, as potential abodes for life. Enceladus presents us with a profound scenario. It seems to have everything life needs to get started. If we go back and find nothing, that discovery would be just as significant as finding life. It would mean that even with all the right ingredients, the spark of life is incredibly rare. But the alternative, the possibility that we could one day detect the undeniable signatures of living organisms in those icy plumes, that's a possibility that could finally answer one of humanity's oldest questions: are we alone? This tiny, icy moon, once a mere footnote, might just hold the key to our cosmic loneliness. The story of Enceladus is far from over.